Hey guys, welcome back to question number 3 of the 2026 AP Chemistry FRQ. Number 3, the following information applies to all parts. Nitrous acid is a weak acid that ionizes according to equation 1. So I'm going to stop and I'm going to put on my equilibrium hat and my Ka, Kb, Kw hat. Okay. Again, what does that mean? That means that I'm going to start kind of changing my brain into thinking about some of the keywords and key concepts that are involved with those kind of things. All right, so moving on. Equation number 1 is essentially a reaction of nitrous acid with water to give you nitrite and hydronium ion and gives you the Ka. Part A, identify the conjugate acid base pair in the equation. Be sure to clearly label which is the acid and which is the base. All right, easy enough, right? We know this is a Bronsted acid. And what happens after it does its thing? This would be our conjugate base. So that's one pair. The other pair would be, since nitrous is an acid, this would be our base. So therefore, our acid, conjugate acid, would be this one. This would be a other pair, right? So that's what you would write down. So let's go to our problem 3. Problem 3, A. Um, you would write 3A. We would say the acid. Why are we not writing? Come on. Oh, I should have restarted my computer, but I didn't. Now I'm paying for it. I should have done that since I did the other questions. But, oh, yeah. What happened? We died. Um, I'm gonna pause you for a second. All right, so bad news is that my PDF crashed, which means I lost everything that I wrote on question 1 and 2. Good news is that it was recorded, so who cares? All right, so we're back. Nitrous acid. Here we go. So conjugate acid base. I know you've seen it on the previous one. I know I had to restart, so I'm just gonna go ahead and just plate this answer. Okay. So this is gonna be 3A, the question 3. Question 3. Come on. Question 3A. And you're gonna have the acid is what? Acid is going to be nitrous, and the conjugate base is going to be our uh, nitrite, which is going to be NO2 minus, right? That's fine. Now you can just write this, or you could have also come up with conjugate acid is your H3O plus, and then our base is H2O. You could also come up with this pair as well, right? And I don't think it actually says to identify the pair, right? It does say it. Clearly label. Oh, so it does say which is acid, which is base. So yes, so either one of these two will be fine. Okay, you don't have to write both. Let's go to B. Um, B, solution of nitrous with an initial concentration of 0.125 molar has a pH of 2.09. Okay. Calculate the value of hydronium in the solution. Show the work that leads to your answer. Okay, so this is where I guess you can make some mistakes, right? So if you decide that you're just going to do a pH equals negative log of the hydronium concentration, um, you're not a P student, are you? Right? Because what do we say here? That's for strong acid. This is for weak acid, right? So let's go try to solve this one. In order to do this, you need to go through the long haul of trying to figure out what is what, I guess, but it's not really necessary, right? Because what we realize is that we were given for part B. I don't know if you guys covered it. I cover it. It's actually optional, right? the Henderson-Hasselbalch equation is probably the best and the fastest way to solve this one. So if you don't, you have to break out Lice charts and go through all that nonsense. But according to Henderson-Hasselbalch, pH is equal to pKa plus the log of base over acid, right? I don't think this is in your reference table. I mean, I don't have the new one. I mean, I'm not used to the new one. It was never on there, so my students had to memorize it. So I told them to memorize it. So yeah, I'm pretty sure. Yep, I don't see it here either. So this is something you should have memorized, right? Oh well, right? So Henderson-Hasselbalch is an easy way to calculate your pH of a weak acid, right? So as long as we're given all the other stuff, right? And in this question, if you go back to equation one, PA is given to us. I'm sorry, Ka is given to us, right? It's 5.6 times 10 to the minus 4. So we have all the values to try to solve this. So if you go to part B, it says solution of HNO2 with an initial concentration of 0.125, right? So according to this, we have your initial concentration of HNO2 at 0.125 molar, right? And then calculate the equation. So we got, um, hmm, we still have to solve for, um, yeah, actually, we still have to solve for values, right? So hold on. So since that's what's given to us, right? Calculate the concentration. So we got, where should we get the numbers from? Let's start plugging stuff in, shall we? So we got negative log of our Ka, which is from the problem 5.6 times 10 to the minus 4. 5.6 times 10 to the minus 4 is our Ka, right? And then to it, we're gonna need concentration of our hydronium, right? Uh, how do we get that? Let's see. Part B. Experiment solution is the experiment. Okay. pH of all right. I'm rereading 3B and 3B1. All right. So little correction here. I kind of jumped the gun with Henderson-Hasselbalch, didn't I? Right. So if you think about this, right, they gave us the pH of a solution. So if you have a pH of a solution already given to you and you're not calculating it, then you can just use the pH calculation. So when I said you're not an AP chemistry student, actually you are an AP chemistry student. So scratch what I said, right? So let's go back to calculating the 3BI, where they want you to calculate the hydronium concentration given the pH. That's really deceptively simple, right? It's I actually can't believe how direct and um not confusing this question is, to a point where I actually confused myself because I thought the question was actually more complicated than I thought. All right, so that's the pH, right? So what do we do? pH calculation is pH equals negative log of our hydronium ion concentration, right? That means our hydronium ion concentration, right, is equal to 10 to the negative pH. And it is this simple, right? And what does that give us? That gives us 10 to the negative 2.09. That gives me a value of 3 sig figs, so it would be 8.13 times 10 to the negative 3 molar. Okay, so that would be the answer So I would copy that right up here, H3O plus is equal to 8.13 times 10 to the minus 3 molar. All that, and let's move on. Part 2. Calculate the nitrous acid concentration at equilibrium. Show that the work leads to your answer. All right, so this one we have to calculate. So this one, I'm going to write HNO2, and they want it at equilibrium, right? At EQ is equal to, let's leave that, and we're going to have to do some ice charts, all right? So start with our equation, HNO2 plus our H2O, yielding our nitrite plus hydronium. All right, what are we guys going here? All right, so now we have this. What do we know? We have the initial concentration of our HNO2, right? If you look in the question, it says, part B, solution of HNO2 is an initial concentration of 0.125 molar. So initial concentration of 0.125 molar is written here. And we don't care about water, right? Because in an equilibrium expression, water doesn't, liquid water doesn't, it's omitted. It's not part of it. All right. And then what else we got? In the beginning, we don't have any of these, right? But we did calculate the pH of the solution, which means that that's the concentration of hydronium at the end. So that would make this 8.13 times 10 to the minus 3 would be right over here. Okay. That means, though, since this is a balanced chemical equation and it's a 1-to-1-to-1 ratio, we also understand that when 8.13 times 10 to the minus 3 moles per liter was produced of the hydronium, so exact same amount of nitrite was also created, right? I'm not going to go in and fill in the rest of this, right? Or maybe I will, right? 8 point, this is unnecessary. This part is unnecessary. This is what you do in class when you want to show that you understand, right? But now what happens? We got the creation of that. So what's the change over here? The change here, since it's 1-to-1 ratio, it's going to be negative 8.13 times 10 to the minus 3 on this side, right? So that means the equilibrium, right? I'm going to just double check that I am still sharing this thing. Okay. All right. So that means that what's happening here is that equilibrium concentration 0.125 minus 8.13 times 10 to the minus 3, right? We good? Right? So that's it. That's our equilibrium concentration is literally that. So now what we're going to do is just solve for it, right? So that is 0.125 minus 8.13 times 10 to the minus 3. What does that come out to? 0.125 minus 8.13 times 10 to the minus 3. I get, with 3 sig figs, 0.117. Right? So I'm going to put 0.117 molar. Circle it. I am done. All right, so let's move on. This was 3B2. Let's look at 3B3C, I guess. 3B1 and 2 is done. Let's go to part C. In an experiment, solution of 0.125 molar nitrous is heated to a new temperature. The new equilibrium concentrations are determined to be such, such, and such. Calculate the value of Ka for HNO2 at 333 kelvins. That's easy. That's just straight plug in. Is the reaction endothermic or exothermic? Justify your values. All right, so let's go. Let's go to 3C1. Right? Here we go. 3C, Roman numeral 1. They want the Ka value, right? So Ka, the new Ka at 333 is going to be what? So Ka is going to be concentration of our NO 2 minus. Is that Ka? Right. It's gonna, where's our equation? I have an equation up here, right? NO2 minus, there we go, times H3O plus all over concentration of HNO2. Are we good? You guys okay? All right, so that's easy. Now, what happens? If you have the problem in front of you, if you take a look, because I'm looking at my other sheet, it says in part C, they do give you the equilibrium concentrations. The concentrations are HNO2 and HNO2 is 0.114. Meanwhile, on the top, nitrous HNO2 minus is 0.0109 and hydronium is also 0.0109. So it's going to be both, this is both going to be 0.0109, right? Like that. That's it. So to solve for this, what do we got? It is the square of 0.0109 squared. That's not squared. Squared, nope, that's not squared either. 0.0109 squared divided by 0.114. That gives me a value of uh, I need to do sig figs, right? 3 sig figs. I'm gonna call it at 1.04 times 10 to the minus 3 as our Ka. Okay, so 1.04 times 10 to the minus 3 is my Ka. All right, so let's go to Roman numeral 2. It's asking, is this reaction endothermic or exothermic? Right? So let's take a look. Justify your answer by comparing Ka values. All right, so let's look at the Ka values. Ka at, what's the first temperature? I'm going to go back to the problem. In the first problem, Ka is at 298. Ka at 298, that's given to us, right? In equation 1 is 5.6 times 10 to the minus 4. All right. And let's look at the new Ka that we calculated. Ka at this higher temperature is going to be 1.04 times 10 to the minus 3. Now you don't need to even look at the first parts, right? It's an order of magnitude of 10 to the minus 4 and 10 to the minus 3, right? So what do we know? We know that Ka at 298 versus Ka at 333, the at Ka 333 is higher, right? It's a larger number. So what does that tell you? That tells you that the since your Ka is products or reactants, right? Right? Ka is concentration of products over concentration of reactants. Therefore, higher Ka at 333 means at higher temp, we have more products, right? So what does that mean? At higher temperature, we have more products, which means that it favors forward reaction, right? So therefore, if you have higher temperature and it actually likes the reaction to go forward, that means that it's an endothermic reaction. Heat is a reactant, right? Right? So heat must be a reactant. Therefore, reaction is endothermic, right? So it's a reaction. So you write the reaction is endothermic because comma, and that's your explanation. All right, we're done with part C, right? And then let's go to D. All right. In a second experiment, student is given a bottle containing a nitrous with an unknown molarity. Determine the concentration of the H channel 2 in the bottle. Student titrates 35 mils of the H channel. This is VA with 16 molar. So that's molarity of our base, which reacts according to equation 2. All right, it's just a titration equation. Results of titration are summarized in figure 1. Using figure 1, identify the pH of the equivalence point. I can't believe how simple this is, right? Equivalence point is what? It's right here, right? That's the steep slope. So what's the pH at steep slope? It's 8, right? So I'm gonna go fill it out later, but let's see. Using figure 1, calculate the molarity of our acid of the bottle. Show the work that leads to your answer. All right. Let's think about this for a second. All right. The first one is easy. The second one is actually just as easy too, right? So we got MA, and then you got MB and VA. We just need volume of the base. Well, check it out. We do have the volume of the base. Isn't this VB, right? So we have everything. So let's go start plating. All right. So 3C, and this is 3D. All right, 3D. The pH is 8.0 at the equivalence point. Okay. And then part E, what do they want you to calculate? Calculate the molarity of HNO2. So they want the molarity of the acid. All right, so let's go. We got MAVA equals MUB, and we're trying to calculate for MA. So you know the titration equation, right? You don't have to write this. I'm doing this, so if you're following along, you could just write it like this, right? Right. All right, so what do we got? Do we have these values? Sure we do. I'm going to go back to what we wrote. Our concentration of our acid is unknown, right? That's our unknown. It says volume, unknown molarity to student titrates 35.0 milliliters. So that's 35.0 milliliters. Molarity of the base is given to us. It says titrated with 0.16 molar NaOH. I'm reading this from the problem. 0.16 molar. And our volume of the base, you read it off the graph. At pH of 8, it was at 50.0 milliliters. All right, so now we just plug in. 0.16 molar times VB is 50.0 milliliters all over 35.0 milliliters. What do we get? We get 0.16 times 50 divided by 35. That gives me 0.26, right? 0.23. 0.23, and that's smaller. Done. Okay, so that's 3 part E. Let's go to part F. Part F is draw an X. So I'm going to say F, C, figure 1. Let's go. It says here, draw an X in figure 1 to represent a point in the titration where acid is greater than base in the reaction mixture. Well, guys, remember this is a weak acid titration, and I hope in your classes you've learned the difference in the graph between a weak acid titration versus a strong acid titration, right? And a weak acid, what do we got? We have a couple of things to note. We have your equivalence point, which is pointed right here, but what else we have? We have what's called halfway point, right? It's also called halfway equivalence point. Halfway equivalence point is literally like smack in the middle of this lower curve where it is possibly going to be the middle of the change of the slope. So it would be like right around here, right? That would be the halfway to equivalence point. What is interesting about halfway to equivalence point? Halfway to equivalence point is where this is your pKa. But what else is important is, or this is where pH equals pKa, right? Why is that? It goes back to the Henderson-Hasselbalch, but you understand here that the concentration of our HNO2 here is equal to our NO2 minus. Or in other words, the way you write it is, right, that's equal to 1. That's a 1-to-1 ratio. What does that mean? That means that's a 1-to-1 ratio right there, where the acid to base is equal to each other. But in the problem, it says it wants you to put an X in a point where there's more acid than base. Well, what do we know? We're adding base, so therefore, we want to be in any point. I'm going to use a big, big color here. Any point that's going to be on the left of that. So any point that you put an X around here should be an acceptable answer. So I'm just going to put it like right there, right? So that's fine. So anything from X-axis of 25 or below is a valid answer in this case, right? Because over here is going to be where it's going to be equal to each other, okay? All right, and let's go to, that's F. F is done, right? E's done, D's done, F is done. Let's go. Part G, equilibrium constants at 298 Kelvin are shown in table 1 for the acid ionization reaction represented by equation 1, Ka. The auto-ionization of water of Kw and the neutralization reaction. Okay, calculate the value of K2 for the equation at 298 kelvins. All right, so let's take a look. This is easy, right? So this is essentially asking if you know how the equilibrium responds when you manipulate the equations, equilibrium equations. So what do we know? Before we get started, let's take a look at what we're looking at. We got HNO2 here, and we got to try to somehow come up with these two equations to end up with our K2, right? Or the equation 2. We notice that HNO2 is on the same side on the equation 1, so we leave that alone. Hydroxide, on the other hand, can be seen on opposite sides. So what do we need to do? We need to keep this, and we need to flip the second equation. All right, so what do we remember? Since we're keeping it the same, so Ka is equal to still Ka. But what's happening to Kw? When you flip the equation, the reverse equation would have an equilibrium that's going to be what? It's going to be 1 over Kw, right? Now what? Now, if you do the first equation with the inverse of the second equation added together is going to give you our K2. And what do we know about adding equations? If you're adding equilibrium equations, what happens to the equilibrium constant? They are multiplicative, right? What can I say that? Right. So which means that K2 is going to be what? Ka times 1 over Kw. All right, that's it. It's that easy. All right, so let's go figure this out. So, going back to write this out, let's see. Does it calculate? It says to calculate, so we have to do it. So let's do it. So this is going to be part G, 3G, right? Is going to be K2 is going to be equal to K1 divided by Kw, right? You don't have to justify, you just have to solve for it, right? So not K1, Ka, right? Ka is 5, oh, it's the same thing. 5.6 times 10 to the minus 4. Our Kw is 1.0 times 10 to the minus 14, right? And what does that come out to? Let's see, 5.6 times 10 to the minus 4 divided by 1 times 10 to the minus 14 gives me 5.6 times 10 to the minus 10. right? So you would say our K2 is equal to 5.6 times 10 to the minus 10. And there's your work. All right. So G's done. Oh, we see the end, right? We see the end. Thank God. H. Student decides to repeat the experiment, this time using an indicator that has access to the indicator in table 2. This is like regions, right? Student conducts a second titration by adding 2 drops of methyl orange indicator, that's right here, to 35 mils of nitrous solution and titrating with a solution of 16 molar. It's all the same thing until the color change from red to yellow occurs. Red to yellow occurs. Student claims that the methyl orange is the best choice for the indicator. Do you agree or disagree? Well, no, why not? Because look, the indicator goes from 3.1 to 4.4, right? And what do we remember, right? You remember from the graph, where's our endpoint? Endpoint is here, right? Endpoint is right here. I don't want to keep writing on this, right? If this is yours, but because it's part of the test. But if you think about it, right? Look at that. The methyl orange goes 3.1 to 4.4. So I'm gonna erase it, but look, methyl orange indicator goes from here to like here. That's what it indicates. So how are you ever going to get to your pH of 8? It's never going to happen, right? So that's the answer. The answer is for 3F, right? The answer is no, right? No, it is not, right? Um, the best choice. Does it ask you to explain? Justify your answer. Okay, so it's because um the equivalence point of the reaction of the titration or reaction is 8.0, and the methyl orange right only goes between what's this, 3.1 to 4.4. The inflection point of the titration, that's the point where it flips between acid and base, right? Is out of the range of the indicator. Okay. Uh, by golly, is this it? Yep, that's it. I think that's it, right? Let me just double check. Yep, that's it. So thank you for hanging with me in question number 3. That was very long, so hopefully it's going to get shorter from here on. And thanks for watching, and I'll see you in the next one.